Now let's put together the last few videos that we've looked at and talk about a specific discrete probability distribution called the binomial probability distribution. What we remember about discrete variables is that they are counted, so they can only take on counting numbers. And if we're going to be able to use a binomial distribution to calculate probabilities for an experiment, then that experiment will have to satisfy the criteria for a binomial experiment. And those criteria are that we would have a finite number of independent trials. And when we use the letter n, we are implying that the value n is not infinite, that it is a finite number. The probability of a success is consistent from trial to trial, and that there are only two possible outcomes. And those outcomes we usually term a success and a failure. And usually when you see in print a solution to a binomial probability problem, you will see a pretty consistent symbolism. N is usually used as the number of trials. X is used to symbolize the number of successes. Little p will be the probability of a success. And little q, which is 1 minus p, the complement of p, would be the probability of a failure. These probabilities can be calculated using this formula. The probability of x successes can be found by this expression, which is the expression for a combination. It's n factorial, n is the number of independent trials, divided by x factorial, so the number of successes, and then n minus x factorial, which will actually wind up then being the number of failures, and then p, little p, raised to the x, little p is the number of successes, and then q raised to the n minus x. So here we have the table from the example that we used where we looked at sampling parts from a selection of thousands of them that would be produced daily, and we were selecting 3. And we constructed this table already where we had the number of good parts. So x was the number of good parts, and it could either be 0, 1, 2, or 3 if we were selecting 3. And then we had the number of ways that we could select 0, 1, 2, or 3 good parts, and that had to do with that probability tree that we had constructed that looked like this, and we can always refer back to that video if we need to refresh about this problem here. So that's where these number of ways came from that tree. And then we calculated those probabilities, or at least we came up with expressions for them, and it led off with this number of ways. And then there was whatever the probabilities along the branch. But let's do the same thing now using this formula. So if x is 0, then this first part of the expression here, so let's recreate this table a little bit here. At least recreate the part that has this coefficient out front. So if x is 0, then n factorial over x factorial times n minus factorial would be 3 factorial. We have 3 trials in that experiment, divided by x factorial is 0 factorial times 3 minus 0 factorial. So this was really then just reduces to 3 factorial over 3 factorial, because 0 factorial is 1 and 3 minus 0 is 3. So this whole thing just turns out to be 1. And then if x goes to 1, then we have 3 factorial over 1 factorial times 3 minus 1 factorial. 1 factorial is also 1, so this thing just reduces to 3 factorial, which is 3 times 2 times 1, over 1 factorial, which is 1, times 2 factorial, which is 2 times 1. The 2's and the 1's cancel, and we wind up with just 3. If x is 2, then we have 3 factorial over 2 factorial times 3 minus 2 factorial, which turns out to be the same thing as the previous one, because we have 2 factorial on the bottom and then 3 minus 2 factorial, which is 1 factorial, which is just 1. So we have 3 times 2 times 1 over 2 times 1. Again, these cancel and we're left with 3. And then if x is 3, we have 3 factorial over 3 factorial times 3 minus 0 factorial, which again is just going to give us 1. So this column here, 1, 3, 3, 1, matches what we found in this tree. So that's what this part then of the formula is doing. It's calculating how many branches of this tree have that particular number of successes. And then the second part here, x factorial, or p to the x, q to the n minus x, if we can fit this in here, is just going to give us these parts here where we have the probabilities multiplied. So if we have p is 0.9, that was the probability of a success. 0.9 raised to the x, if x is 0, that really just becomes 1. And then we have q, and if p is 0.9, q is 0.1. Raised to the n minus x, if n is 3 and x is 0, that just becomes 3. Which is the same then as what we have here when we just figured this out using the tree. And this is going to continue on down like this. So that's how this formula works.